We now come to the fourth of the classification techniques we are going to consider in this course. We will develop it in two stages, in its original form and its return in a more powerful and flexible form over the past 5 to 10 years. The neural network, sometimes called the artificial neural network, was popular in remote sensing in the 1990s, but because it was complex to design and required significant computational power, it was overtaken by other techniques such as the support vector machine. However, with some simple modifications that lead to improvements in performance and training, it has gained popularity again over the past decade. Now called convolutional neural networks, these later variants also go under the name of deep learning, although that description could just as easily have applied to the neural network in its original form. As with the support vector machine, we start by a return to the simple linear classifier. Again, we will do our development with a simple two-dimensional two-class situation, but it will generalize to any number of classes and dimensions. And again, we use our standard decision rule for linear decisions, which we will now represent diagrammatically in the form of what is called a threshold logic unit, or TLU. In this diagram, the elements up to the thresholding block create the linear function used in the decision rule. The thresholding operation then checks whether the value of the function is positive or negative, and thus whether the pixel vector is in class 1 or class 2 as required by the algebraic expression of the decision rule. Sometimes we represent the overall operation by the single block called the TLU. As noted on the previous slide, this was one of the building blocks used in early machine learning theory that led to a classification machine called the perceptron. It is also where we start the development of the neural network. A breakthrough came when the hard limiting operation in the TLU was replaced by a softer function, and in particular, one that could be differentiated. As we will see, that allows a training procedure to be derived which is not otherwise possible. We call the soft limiting operation an activation function. Typical examples include the inverse exponential operation, or sigmoid, and the hyperbolic tangent, as shown in this slide. As seen, the behavior still represents what we want in terms of specifying the class to which a pixel belongs, because it implements our decision rule, but without a hard limit. The old TLU, but with a soft limiting operation, is now called a processing element, or PE. In the nomenclature of neural networks, we also replace the offset W subscript n+1 by the symbol theta. Note in the bottom right-hand drawing that we will write the output of the processing element as g equals a function of z, where the function f is the chosen form of the activation function and z is the linear function in our normal decision rule. The classical neural network, and that which was applied widely in remote sensing, is called the multi-layer perceptron, or MLP, and is composed of layers of processing elements which are fully connected with each other, as seen in this slide. The blocks in the first layer are not actually processing elements. They just distribute the input pixel vector elements to each of the processing elements in the next layer. The outputs of those processing elements then form the inputs to another layer of PEs, and so on, for as many layers as chosen by the user. The outputs from the last layer of PEs determine the class of the pixel vector fed into the first layer. Now the user can choose how that is done. Options are that each class could be represented by a single output, or the set of outputs could represent, for example, a binary code that specifies the class. Note the nomenclature used with the layers of a neural network. In particular, the first layer, which does any real analysis, is the first hidden layer. Note also the letter designations we apply to the layers. And while we have shown only one, there can be many hidden layers, each being fed from the outputs of the previous layer. As the number of hidden layers increases, training the neural network becomes increasingly time-consuming. In many remote sensing exercises of several decades ago, only one hidden layer was used and found sufficient to handle many situations. But training still took a long time, as we will see later. Having chosen a topology, we now need to work out how to find its unknown parameters, that is, the weights W and the offsets theta for each processing element. As with all supervised classifiers, that is done through training on labelled reference data. But to make that possible, we need to understand the network equations so that a training process can be derived. That is now our immediate objective. The equations describing each processing element are those we noted earlier, that is, G is a function of Wtx plus theta, and remember Wtx plus theta is the linear function. However, we need a naming convention to keep track of where the inputs come from and where the outputs go. We do that by adding subscripts to the weight and offsets as shown here. Our nomenclature is simplified in that it is layer specific but not PE specific. We could add a third subscript to indicate each actual PE in a layer, but that turns out to be unnecessary. We can derive the relevant network equations for training without going to that added complexity. To start developing our training procedure, we need a measure of what we are trying to achieve. Clearly, if the network is functioning well as a classifier, we want the output to be accurate when the network is presented with a previously unseen pixel vector. We check the network's performance by setting up an error measure, a measure that looks at how closely the actual output matches what we expect when a training pixel is fed into the network. We choose for that measure the squared difference error measure shown in the center of this slide. Remember, the set of actual outputs of the network are G subscript K. This measure tells us how well those actual outputs match the desired or target outputs T subscript K for given training pixel vectors. In the next lecture, we will use that expression to help set up the necessary equations with which we can train the neural network. Clearly, our objective is to find the unknowns, weights and offsets, that minimize the error measure. In other words, that make the actual class labels match as nearly as possible the correct or target labels. In this part of the course, we are examining the use of the popular multi-layer perceptron as a classifier in remote sensing. It consists of layers of processing elements where each PE contains a differentiable activation function. We are now at the stage where we can set up the network equations. The second question here is important because it starts to develop a feel for the complexity of training a neural network.